Hey everybody. So now we're going to take a look at a BC topic. This frankly could be an AB topic, but it's on the BC exam. And this is how to find the length of a curve. Now you should know how to find arc lengths of circles. Obviously that's just fractions of the circumference of a circle. But obviously not all functions are circles. So we've got crazy, twisty, windy functions that we've been studying all this year and last year. So let's explore how to find the length of a curve. You're going to need your graphing calculator in a second, and we're going to do a couple examples. And you also need your foldable so you can put a brand new formula on it. All right, let's explore. All right, so if we want to approximate the length of a curve, just approximate it, what we could do is just to find that distance, well, we can make ourselves a little right triangle. And we have it some change in x and some small change in y. And obviously we could do a quick little Pythagorean theorem. Well, if I wanted to get a better approximation, what I would want to do is to make a smaller little triangle inside of there so that there was the length of the curve and the length of the hypotenuse would approach the same length. And so I want to make those smaller and smaller and smaller. So first of all, by the Pythagorean theorem, so the length of the arc squared equals the sum of the two sides squared, our Pythagorean theorem. So if I solve for the hypotenuse, I get this expression here. But what I want to do is I want to sum up an infinite number of small little hypotenuses, and that's the plural, hypotenuses along the curve along a closed interval. Well, what do I use in calculus to sum up infinitesimally small little amounts? Well, I'm using an integral. So I'm going to introduce the integral of both sides. And the integral also we can see here of ds is going to be s on the left. But then what we need to do is I want to get the dx out of the radical here because again, for a differential equation, before I anti-differentiate, I need a dx on the outside. So I'm going to divide through by dx squared for both terms and then also multiply by dx squared. So this is not changing the value of the expression. And now you can see that dx squared on the right here, it's going to then can be factored out underneath the square root. We see dx squared over dx squared is just going to be 1. And then I have dy dx squared. So also notice on the left, the antiderivative is just s. And then so I wind up in the end getting my integral here for the length of the curve. So the length is the integral. Now we don't have a plus c here because we're going to do it over a closed interval from a to b. So it is the square root of 1 plus the derivative squared, dx. Now yes, can we do this then in terms of y and find if the function was given to us in terms of y? Sure. And then I'm just going to have a dy and my interval is going to be in terms of y's. So you want to make sure, maybe pause me quick here and get this onto your foldable. This is the length of a curve. Now, I'm mentioning this is the Cartesian because we are also going to learn a parametric form of this later on, and we're going to come back and revisit this second to the last step here. You can almost see what's going to eventually happen. Instead of dividing through by dx squared, we're just going to divide through by dt squared for a parametric curve. But at least for now, simple little formula, make sure you jot it down. Let's look at an example or two. Okay, so let's take the function negative x squared plus 9 on the closed interval from 0 to 3. And I want to know what is the length of this arc. Okay, we're not going to approximate it here. We're actually going to evaluate it. So the first thing I got to do based upon the formula is I got to take the derivative. And then I can set up my integral. So I'm going from 0 to 3. Those are x values because I'm in terms of dx and substituting in my derivative. And then maybe just doing a little simplification. Now at this point, in terms of anti-differentiating this, I can't use chain rule. It's not partial fractions. It's not integration by parts. I'm not quite sure how to do this. There are some techniques to play around with in terms of creating and completing the square to create a perfect square underneath of that radical so that I could square root it. The square root's typically the problem in this. And there'll be some examples that we'll try to play around with here over the next day or two. They typically are not asked to do that on the AP exam. So what we're going to wind up using on the AP exam is our graphing calculator. So just a simple math 9 evaluating, and I get about 7 3/4 in length. So let's compare this quick, and again, simple antiderivative, or sorry, simple definite integral we've done before in our calculator. But let's see if I did connect it with a straight line. So a little Pythagorean theorem, 9 squared plus 3 squared is c squared. And so I'd get the square root of 90, which is about 9.49. And you can see clearly that's much less than the 9.74. And obviously, because of this graph being concave down, we're going to get this approximation being a little bit shorter. So 9.49 is an approximation, whereas 9.747, or at least the whole value there, that is the exact length of that curve. So we can also use our graphing calculator to even take the derivative. Now, this example seems a little silly, but what I would do is have my function in my y1, and again, the function could be really messy, or really hard, or very cumbersome to differentiate. So just put the function into y1, and then on my home screen, I'm gonna do a math 9, I'm gonna do a definite integral from 0 to 3, and then I'm gonna do the square root of 1 plus, and then the derivative of what's in y1 at every x value, x equals x. Typically they want to have at x equals a specific value to evaluate the derivative at a point. Well, I'm saying to take the derivative at every x value, and then just be careful, you need a set of parentheses to square that derivative value. And hitting enter, and then you get 9.747 again. So this is going to be a typical way. Especially if this is in a free response problem, you probably already have the function in your y equals, so why not use it to your advantage? Plus it makes writing this definite integral on your calculator a lot cleaner and easier. You're not typing in a whole big derivative of a function, which could involve product rule and quotient rule and chain rule and all kinds of stuff. So a neat little trick. One little fun thing to end on here is let's find the length of this arc. So it is the arc of a semicircle. So in fact, if you think about it real quick, we'll do a quick little calculation in your head. What's the length of a half of a circle with a radius of 1? 2 pi r, 2 pi times 1. All right. So I got to first solve for y. So we got the square root, just the positive square root. I'm only doing the upper half. And then into my graphing calculator. Again, I'm not going to take the derivative on my own. I'm just going to let my calculator evaluate the derivative like I just showed you. And lo and behold, 3.14, you get pi. So you can almost see how we could, and it's something interesting if you're interested in taking a look. You could use the length of a arc formula to then develop the arc length formula for a circle. If you play around with that, you could play around with this situation. The hard part with these is actually trying to anti-differentiate that square root, but it's all about creating a perfect square underneath of that radical so that you can get rid of that radical and then anti-differentiate. So make sure you take a look at the 2 other examples from the AP Classroom, because they are showing you some specific examples of what this will look like on the AP exam. All right, good luck, guys.